What if everything you thought you knew about time was just the tip of the cosmic iceberg? Time isn't just the ticking of a clock or the pages of a calendar. It's a wild, twisting, unpredictable force that bends and warps under the weight of the universe itself. Picture this: a single second here on Earth could stretch into an eternity near a black hole, or vanish in a blink near the speed of light. Time isn't just passing, it's dancing, swirling, and playing tricks on reality in ways that defy human intuition. And that's just the beginning. Today, we're diving into the deepest mysteries of time, exploring 30 mind-bending facts that will shatter your perception of reality. From the way gravity slows time down to the eerie possibility of parallel universes where time flows backward, these aren't just abstract ideas. They're the hidden rules that govern everything from the birth of stars to the fate of our own existence. You'll discover how time might not even be real in the way we think it is, how the past, present, and future could all exist simultaneously, and why some scientists believe the entire universe might be a single, frozen moment in time. This isn't just a video, it's a journey into the heart of one of the universe's greatest enigmas. By the end, you'll never look at a clock the same way again. So buckle up, because we're about to unravel the fabric of time itself, piece by astonishing piece. Are you ready to have your mind stretched to its limits? Let's begin. Let's start with a fact so strange it sounds like science fiction. Time itself slows down near a black hole. Imagine you're floating in space, watching a clock inch closer to the black hole's edge. As it nears the crushing grip of gravity, something bizarre happens. The seconds drag longer and longer, ticking slower and slower compared to your own watch back on Earth. This isn't some glitch, it's the universe obeying Einstein's theory of relativity, which tells us gravity doesn't just pull on objects, it warps time itself. Think of space like a stretchy fabric and a black hole like a bowling ball sinking deep into it. The heavier the object, the deeper the dent, and the more time stretches around it. Near a black hole's event horizon, the point of no return, time bends so dramatically that a single minute there could equal years back home. Astronauts orbiting Earth even experience this on a tiny scale. Their clocks run slightly faster than ours on the ground because Earth's gravity is weaker farther out. But near a black hole, the effect is extreme. If you could hover just outside one, watching from a safe distance, you'd see someone falling and move slower and slower, like they're stuck in cosmic molasses until they seem to freeze in place. Here's the wild part: time doesn't just feel slower, it is slower. For the person falling in, their own clock ticks normally, but from the outside, their entire existence stretches into what looks like an endless pause. This isn't an illusion, it's the universe revealing time as something fluid, something that twists and bends under the weight of gravity. So next time you glance at your watch, remember, time isn't rigid. It's a shapeshifter, and black holes are proof that the universe plays by rules far stranger than we ever imagined. But here's where things get even weirder: time isn't just warped by gravity. It's also stretched and squeezed by speed. Take the famous twin paradox, where one twin rockets off into space at near light speed while the other stays on Earth. When the traveling twin returns, they've aged far less than their Earth-bound sibling. This isn't some hypothetical thought experiment. It's real physics confirmed by ultra-precise atomic clocks on fast-moving jets and satellites. Time literally flows slower the faster you go. Picture space as a vast ocean and time as the current. If you're standing still, floating with the flow, your clock ticks normally. But the moment you start swimming against the current, fighting against the fabric of space-time itself, your experience of time changes. The harder you push, the closer you get to light speed, the more the universe resists, slowing your personal clock compared to everyone else's. This is relativity in action. There's no universal now, no single clock that ticks for the entire cosmos. Your experience of time depends entirely on where you are and how fast you're moving. Now imagine two clocks, one on a speeding spaceship, one on Earth. From Earth's perspective, the ship's clock runs slow. But here's the twist: from the ship's perspective, Earth's clock is the one lagging behind. Both observations are correct because time isn't absolute. It's a personal experience, bending to match your journey through the universe. This means astronauts on the International Space Station, zipping around Earth at thousands of miles per hour, are technically time travelers, albeit by fractions of a second. So why don't we notice this in everyday life? Because at human speeds, the effect is vanishingly small. But crank up the velocity to near light speed, and the differences become impossible to ignore. A 5-year trip at 99% light speed could mean returning to an Earth that's aged decades. The universe doesn't care about our human sense of simultaneity. It plays by its own rules, revealing time as something deeply personal, malleable, and utterly bizarre. The next time you check the clock, remember, your now might not be someone else's now at all. What if time isn't flowing at all? What if the past, present, and future exist simultaneously, like frames frozen in a cosmic film reel? This is the startling idea behind the block universe theory, a radical perspective that turns our everyday experience of time on its head. Instead of a river flowing from one moment to the next, the universe might be more like a vast, unchanging block where every event from the Big Bang to the distant future already exists locked in place. Think of it like a DVD. When you hit play, the movie unfolds scene by scene, giving the illusion of movement and change, but the entire film is already there, encoded on the disc. In the block universe, reality works the same way. Your birth, this very moment, and everything that will ever happen are all equally real, just occupying different slices of the cosmic block. This isn't science fiction, it's a legitimate interpretation of Einstein's equations, which treat time as just another dimension, like space. Just as you can move left or right in space, time might simply be another direction in which the universe extends. Some physicists, like Carlo Rovelli, take this even further. They argue time might not even be fundamental, it could emerge from the chaotic interactions of quantum particles. Picture a boiling pot of water. The bubbles and movement create the illusion of activity, but beneath the chaos, there's no single flow of time, just countless tiny interactions. At the deepest level, time might be nothing more than a useful fiction our brains construct to make sense of the universe's complexity. Here's where it gets truly mind-bending. If the block universe is real, free will starts to look like an illusion. Every choice you've ever made, every action you'll ever take, might already be set in stone, part of the unchanging fabric of space-time. But don't despair. This doesn't mean life is meaningless. Even if the future is already there, your experience of it, the joy, the struggle, the discovery, is still uniquely yours. The block universe doesn't erase your story. It simply suggests that the story might be bigger, stranger, and more interconnected than we ever realized. So the next time you feel the weight of a deadline or the rush of a ticking clock, remember, time might not be what it seems. It could be a trick of perception, a cosmic sleight of hand hiding the true nature of reality. Whether it's an illusion or not, one thing's certain: the universe has far more secrets to reveal about the nature of time, and we're only just beginning to unravel them. Time travel isn't just the stuff of science fiction. It's a real, provable phenomenon, and you don't need a DeLorean to do it. Thanks to Einstein's theory of relativity, we know that hurtling through space at near light speed or orbiting a black hole could catapult you into the future. Imagine boarding a spaceship capable of 99% the speed of light. A 5-year journey for you might mean returning to an Earth that's aged 50 years. Your friends and family would have moved on without you, while you'd barely feel the passage of time. This isn't speculation, it's physics in action. Take the movie Interstellar as an example. Remember Miller's planet, where every hour spent on its surface equals 7 years back on Earth. That's not Hollywood exaggeration, it's science. The planet orbits so close to the supermassive black hole Gargantua that its gravity warps time to an extreme degree. For the astronauts, a quick trip to the surface feels like minutes, but by the time they return, decades have passed for everyone else. This phenomenon, called gravitational time dilation, means that time slows down the stronger the gravitational pull you're experiencing. But here's the catch. While this kind of time travel lets you leap into the future, there's no going back. The universe has strict rules. Moving forward is easy. Reversing time is another story entirely. Even if you could build a ship fast enough to approach light speed, you'd need impossible amounts of energy. And orbiting a black hole, one wrong move and you're spaghettified by tidal forces before you even get close. Yet the fact remains, the laws of physics don't forbid time travel to the future. We've already seen it on a tiny scale with astronauts on the International Space Station, who come home ever so slightly younger than if they'd stayed on Earth. So why aren't we all jetting off to the future? Practicality, mostly. The energy required to reach such speeds is beyond our current technology, and the risks of dancing with black holes are well cosmically high. But the universe doesn't care about our limitations. It whispers a tantalizing truth: time is fluid, and under the right conditions, the future isn't just a destination, it's a place you can visit if you're bold enough to try. The universe didn't start with a slow fade in, it exploded into existence with a fireworks display of physics so extreme, our laws of nature can't even describe it. The first fraction of a second after the Big Bang, known as the Planck epoch, was a realm where time itself didn't behave the way we understand it today. Picture this: temperatures so high that matter and energy were indistinguishable. Gravity was just another force jumbled with the rest, and the very fabric of reality flickered in and out of existence like static on a cosmic TV screen. This was a time, if you can even call it that, where the clock didn't tick, it stuttered. Then came inflation, a burst of expansion so violent it makes today's universe look like it's standing still. In less than a blink of an eye, space ballooned from smaller than an atom to trillions of miles across, faster than light itself. That's right, the universe grew at speeds that would make Einstein raise an eyebrow. How? Because the speed limit of light applies to objects moving through space, not to space itself stretching. Imagine dots on a balloon. As you inflate it, the dots move apart, but they're not actually traveling. The fabric between them is expanding. Inflation did that to the entire cosmos, and it happened in a fraction of a second, so tiny, we struggle to comprehend it. Here's the wild part: during inflation, quantum fluctuations, tiny ripples in the newborn universe got stretched to cosmic proportions. Those microscopic wobbles became the seeds for everything we see today: galaxies, stars, even the voids between them. Without that explosive growth spurt, the universe might have collapsed back on itself or torn apart too quickly for life to ever emerge. Inflation didn't just shape space, it set the stage for time to flow in a way that would eventually allow clocks to tick, planets to form, and you to exist. So the next time you glance at a clock, remember, the very notion of seconds, minutes, and hours is only possible because of that unimaginably chaotic first moment. Time didn't just start, it had to fight its way into existence through a storm of energy and expansion that defies everything we know. And somehow, against all odds, it settled into the steady rhythm we rely on today. But don't be fooled, time's normalcy is just a temporary calm in the cosmic storm. The universe hasn't forgotten how to bend the rules, it's just waiting for the right moment to remind us. Somewhere in the distant future, time itself could vanish in the most violent way imaginable, not with a whimper, but with a scream. This is the Big Rip, a nightmare scenario where the accelerating expansion of the universe doesn't just continue, it spirals out of control, tearing space-time apart atom by atom. Picture dark energy, that mysterious force pushing galaxies apart, growing stronger over billions of years until it overpowers gravity, then electromagnetism, even the nuclear forces holding atoms together. First, galaxies would rip free from one another, then stars would disintegrate, planets would unravel, and in the final moments, molecules, atoms, even the fabric of reality would shred into nothingness. Time wouldn't just stop, it would cease to have any meaning at all, because there'd be no space left to measure it in. But the Big Rip isn't the only grim finale on the universe's menu. There's also the Big Crunch, a cosmic do-over where gravity finally wins, reversing expansion and pulling everything back into a singularity. Imagine hitting rewind on the Big Bang, galaxies crashing together, temperatures skyrocketing, all of existence collapsing into a searing point of infinite density. Time wouldn't just end here, it might loop, with some theories suggesting a new universe could bounce back from the collapse. Then there's heat death, the slowest and coldest option. Here, the universe keeps expanding forever, but stars burn out, black holes evaporate, and all energy spreads so thin that motion becomes impossible. It's not a dramatic explosion, just an endless, silent freeze where time becomes irrelevant because nothing changes, nothing happens ever again. What makes the Big Rip uniquely terrifying is its intimacy. Unlike the Crunch's grand collapse or heat death's quiet fade, the Rip would invade the microscopic realm, dismantling reality from the inside out. One moment you'd exist. The next, your very atoms would be torn asunder. And because the universe's expansion is accelerating, this scenario hinges on dark energy's behavior, something we still don't fully understand. Will it strengthen over time, or is today's gentle push its final form? The answer decides whether time ends with fire, ice, or something infinitely stranger. Here's the twist: these aren't just grim fantasies, they're real possibilities etched into the equations of cosmology. The fate of time depends on forces we can't yet see or measure, dark energy's secrets, gravity's long game, even the shape of space-time itself. So while the Big Rip might sound like a sci-fi apocalypse, it's a reminder of how fragile our cosmic clock really is. Time had a beginning, and if the universe has its way, it might just have an ending too. Up in the International Space Station, astronauts aren't just floating, they're time travelers, not in the flashy, superhero sense, but in a very real, measurable way dictated by Einstein's equations. Because time runs faster where gravity is weaker, astronauts orbiting Earth actually age slightly slower than the rest of us down here. We're talking microseconds, sure, but those fractions of a second prove something extraordinary. Time isn't just passing. It's bending to the whims of gravity and motion in ways that defy our everyday intuition. Think of Earth's gravity like a heavy blanket pressing down on space-time. The closer you are to that weight, the more time slows like a clock submerged in molasses. But float 250 miles up where the ISS orbits and that blanket thins. Gravity's grip loosens and time speeds up ever so slightly. Over 6 months in space, an astronaut might gain about 5 milliseconds compared to someone on the ground. That's barely enough to notice, but it's enough to confirm relativity isn't just theory, it's etched into the universe's behavior. Now, here's where it gets practical. GPS satellites have to account for this effect every second of every day. Flying 12,000 miles above Earth, they experience even weaker gravity, and their onboard clocks tick faster than ground-based ones by about 38 microseconds per day. If engineers didn't correct for this, GPS locations would drift by miles within minutes. That's right, your phone's map app only works because we've hacked time itself, tweaking satellite clocks to compensate for relativity. So why don't astronauts return home noticeably younger? The speed of the ISS actually counteracts some of the gravity effect. Orbiting at 17,000 miles per hour, their velocity slows their personal time, an opposing twist of Einstein's laws. It's a cosmic tug of war. High speed says slow down, weak gravity says speed up, and the result is a tiny net time gain, but the implications are enormous. Every time we launch a satellite or send humans into orbit, we're not just exploring space, we're negotiating with time itself. And that negotiation reveals a humbling truth: there's no universal correct time. Your clock ticks differently on a mountain than in a valley, in a jet than on a park bench. Even your head ages slightly faster than your feet thanks to gravity's subtle gradient. Time isn't a rigid scaffold holding up reality. It's fluid, personal, and intimately tied to where you stand and how you move through the universe. The next time you check the clock, remember, it's not just ticking. It's telling your own little slice of spacetime's grand, elastic story. Time only seems to move in one direction because the universe has a strict rule against cleaning up its own mess, and that rule is called entropy. Picture a raw egg rolling off your kitchen counter. The moment it hits the floor, there's no going back. The yolk splatters, the shell shatters, and no amount of wishing will reassemble it into a perfect whole. That irreversible chaos is entropy in action, the universe's tendency toward disorder, and the hidden force behind why we remember the past but not the future, why coffee cools but never spontaneously reheats itself, and why time feels like a one-way street. This isn't just about broken eggs. Entropy is baked into the fundamental laws of physics, specifically the second law of thermodynamics, which states that in any closed system, disorder always increases over time. Think of a freshly shuffled deck of cards. It might start neatly ordered, but as you play, the cards scatter into randomness. That's the universe on a cosmic scale. Everything from stars burning out to glaciers melting follows this irreversible slide from order to chaos. Even you right now are contributing to the universe's entropy. Every breath you exhale spreads heat energy into the air. Every movement scatters molecules further apart, and every thought burns calories in a way that can never be perfectly undone. Here's the twist: entropy doesn't just describe time's arrow, it defines it. At the quantum level, the laws of physics are almost entirely reversible. A collision between two particles could run backward and still make sense mathematically. So why doesn't it? Because entropy creates an asymmetry. There are countless ways for particles to be disordered, like the scrambled egg, but only a handful of ways for them to be perfectly ordered, like the unbroken egg. The universe statistically favors mess over neatness, which is why time's flow feels so stubbornly forward. But what if you could reverse entropy? Hypothetically, if every atom in that shattered egg could be guided back to its exact original position, you'd witness time running backward. The catch: the energy required to meticulously rearrange every particle would generate even more entropy elsewhere, keeping the universe's total disorder on its relentless climb. Even black holes, the ultimate cosmic vacuum cleaners, don't escape this law. They devour matter and energy, but their event horizons radiate heat, spreading entropy further into the void. This means time's arrow isn't just a feature of reality, it's a byproduct of the universe's obsession with disorder. Without entropy, cause and effect would blur, memories could unscramble, and the past might as well be the future. So the next time you spill your coffee or drop a plate, don't get frustrated. You're not just witnessing chaos, you're watching time itself unfold, one irreversible moment at a time. Imagine a clock that never winds down, a structure that keeps perfect time without batteries, springs, or any energy input at all. This isn't a fantasy, it's a time crystal, one of the most bizarre and revolutionary discoveries in modern physics. Unlike anything else in nature, these quantum systems don't just exist in space, they pulse rhythmically in time, like a heartbeat that never fades, defying the laws of thermodynamics as we know them. Normally, perpetual motion is impossible. Friction, resistance, and entropy ensure that every machine, no matter how efficient, eventually grinds to a halt. But time crystals operate in a quantum loophole, created in labs using ultra-cold atoms or specially arranged electrons. They don't move through space instead. Their internal structure oscillates between states indefinitely, like a cosmic pendulum that never loses momentum. The secret: they're not powered by energy, They're locked in a quantum dance that requires no fuel, existing in what scientists call a non-equilibrium phase of matter. Here's what makes them even stranger. Time crystals break time symmetry, a fundamental assumption that the laws of physics work the same whether time flows forward or backward. Drop a ball and the motion looks identical in reverse, but time crystals have a built-in rhythm that picks a preferred direction in time, ticking like a metronome that can't be rewound. This discovery sent shockwaves through physics. Nobel laureate Frank Wilczek, who first theorized their existence in 2012, faced skepticism until experiments in 2017 proved him right. Practical applications, they're still emerging, but time crystals could revolutionize quantum computing. Their stability against disturbances makes them perfect for error-resistant qubits, the building blocks of next-gen computers. And on a cosmic scale, they hint at phenomena we've yet to imagine, structures that might exist in neutron stars or even the fabric of space-time itself. So next time you check a clock, consider this. Somewhere in a lab or maybe deep in space, there's a tiny crystal ticking away, not because it's counting time, but because time itself is woven into its existence. The universe just got a little stranger and a lot more fascinating. You might think time dilation only happens at cosmic speeds or near black holes, but the truth is, it's ticking away right in your pocket. Your smartphone's GPS relies on corrections for time dilation. Otherwise, it would guide you into a lake instead of the nearest coffee shop. This isn't a hypothetical glitch. It's a daily negotiation with Einstein's relativity, proven decisively by the Hayfel-Keating experiment in 1971. Scientists flew atomic clocks around the world on commercial jets, comparing them to clocks that stayed grounded. The result, the traveling clocks disagreed with Earth-bound ones by fractions of a second, exactly as relativity predicted. Here's how it breaks down. The faster you move through space, the slower you move through time. Jetliners cruising at 500 miles per hour might seem sluggish compared to light speed, but over enough distance, the effect adds up. A New York to London flight stretches time just enough that, over a lifetime of frequent flying, you'd age about 1 microsecond less than if you'd stayed home. Tiny, yes, but the fact that we can measure this with pocket-sized atomic clocks proves time isn't rigid. It's as flexible as the altitude of your flight. Now consider your GPS. Satellites orbit at nearly 9,000 miles per hour, making their onboard clocks tick slower due to speed. But they're also 12,000 miles above Earth, where weaker gravity makes clocks tick faster. These effects battle it out, with gravity winning by about 38 microseconds per day. Without correcting for this, GPS locations would drift by 6 miles daily. So every time you check your map, engineers have already tweaked the system to account for time's warping. Your phone literally couldn't find itself without bending the rules of reality. What's wild is that this isn't futuristic tech, it's mundane infrastructure. Planes, satellites, even stock markets synchronizing trades all dance with time dilation. The universe whispers its secrets in microseconds, and we've learned to listen. Next time you glance at a clock mid-flight, remember, you're not just traveling across time zones, you're bending time itself 1 mile per hour at a time. The present moment you think you're experiencing, it's already ancient history. Every sight, every glimmer of light reaching your eyes is a message from the past, some fresher than others, but all hopelessly outdated. Consider the stars. When you gaze at Orion's belt, you're not seeing those stars as they are tonight, but as they were centuries or even millennia ago. The closest star system, Alpha Centauri, its light takes over 4 years to reach us. If it exploded tomorrow, we wouldn't know until 2028. Even our own sun is a time traveler. What we see as its current position is actually where it was 8 minutes and 20 seconds ago. If it vanished right now, Earth would keep basking in its light, blissfully unaware for those same 8 minutes before darkness fell. This delay isn't just a quirk of astronomy, it's woven into your daily reality. The screen you're watching this on, the light from its pixels takes a sliver of a nanosecond to hit your eyes, meaning you're always perceiving the screen as it was a vanishingly tiny moment ago. Sound travels slower still at a concert. The guitarist's notes reach your ears milliseconds after their fingers pluck the strings. In a thunderstorm, you see lightning before hearing thunder because light outpaces sound by nearly 1,000,000 times. Your brain stitches these mismatched signals into a coherent now, but the truth is you're living in a carefully constructed illusion of simultaneity. Einstein shattered the myth of a universal present with relativity, proving that now depends entirely on your frame of reference. Imagine two astronauts passing each other at near light speed. One might perceive events on Earth as happening years apart, while the other sees those same events as simultaneous. Neither is wrong. Time itself stretches and compresses based on motion and gravity. This means the present isn't a fixed slice of reality. It's more like a patchwork quilt of overlapping pasts, each observer stitching together their own version of now. Here's where it gets haunting. If you could see Earth from a planet 10,000 light-years away, you might witness pyramids being built or ice age glaciers creeping across continents. The light carrying those images has been traveling through space all this time, a cosmic DVR playing history on delay. Yet from our perspective, those events are long gone. This raises a spine-tingling question. Is there any true present at all, or is the universe just an infinite collage of pasts, each observer trapped in their own lagging snapshot of reality? Your brain works overtime to hide this chaos. It syncs up sight, sound, and touch into a seamless experience, editing out the delays. But the universe has no such courtesy. It broadcasts every event at light speed, no instant replays, no live feeds. So the next time you check the time, remember that clock is lying to you. The numbers you see aren't now, they're the clock's past. Lights traveled time ago in a universe where the present is always just out of reach. At the smallest scales of the universe, time might not just bend, it could vanish entirely. This startling possibility comes from the Wheeler-DeWitt equation, a mathematical framework that attempts to merge quantum mechanics with general relativity. When physicists crunch the numbers, something bizarre happens. The variable for time drops out completely. It's as if the equation is telling us that at the quantum level, time isn't just frozen, it's fundamentally absent. Imagine flipping through a book only to discover the pages aren't numbered, arranged in any order, or even following a sequence at all. That's the reality this equation suggests for the quantum realm, a realm where before and after might not apply. This doesn't mean particles are stuck in limbo. Instead, they could be making quantum leaps through what we perceive as time. Take quantum tunneling, where a particle seemingly teleports through an energy barrier it shouldn't be able to cross. In classical physics, this would be like a ball rolling up a hill and suddenly appearing on the other side without climbing it. Now imagine that hill is time itself. Some theories suggest particles might tunnel not just through space, but through temporal barriers, effectively jumping between moments like a needle skipping across a vinyl record. What would this look like in practice? Picture an electron in an atom. Normally, it occupies specific energy levels like rungs on a ladder, but occasionally it vanishes from one rung and reappears on another without passing through the space or time in between. If this can happen to particles, could entire atoms, molecules, or even larger objects perform similar feats? The math doesn't rule it out, though the probabilities become vanishingly small for anything bigger than a few particles. Still, the mere possibility reshapes our understanding of time from a steady stream into something far more fragmented and unpredictable. This gets even stranger when you consider quantum entanglement, where particles become linked across vast distances, instantly influencing each other's states. If time doesn't exist at this scale, could entanglement also bridge moments in time, not just space? Some interpretations suggest entangled particles might be communicating across what we perceive as past, present, and future, hinting that time's arrow could be more like a web of interconnected events. The implications are profound. If time dissolves at quantum scales, then our experience of its flow might emerge from something deeper, a collective effect of countless quantum interactions, like the illusion of movement in a flipbook. The Wheeler-DeWitt equation doesn't just challenge our assumptions, it erases the clock entirely for the universe's tiniest building blocks. So the next time you check your watch, remember, those ticking seconds might be a cosmic mirage, a shadow cast by a timeless quantum world playing by rules we're only beginning to fathom. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic cycle? Some physicists propose that time didn't start 14 billion years ago but extended infinitely backward, with our universe simply rebounding from the collapse of a previous one. This is the essence of loop quantum gravity's Big Bounce theory, where the singularity of the Big Bang wasn't a true beginning but a turning point, like a cosmic heartbeat, with universes expanding and contracting in an eternal loop. Imagine a black hole's crushing density not as an end but as a seed. When the prior universe collapsed, its energy didn't vanish, it rebounded, birthing our own universe in the process. The math behind this is as elegant as it is mind-bending. Loop quantum gravity suggests spacetime isn't smooth but made of tiny, indivisible quanta. Think of them as pixels of reality. Near the Big Bang, these pixels prevent infinite density, acting like a quantum trampoline that bounces the collapsing universe outward again. There's no singularity, no true zero point, just an endless cycle of expansion and contraction. If this sounds radical, consider the echoes that might linger from the prior universe. Cosmic microwave background radiation, the afterglow of the Big Bang, shows faint anomalies some researchers argue could be scars from a pre-Big Bang universe, like cosmic fingerprints pressed into the fabric of spacetime. But what if there wasn't just a previous universe? What if there was no before at all? Enter the no-boundary proposal, championed by Stephen Hawking and James Hartle. Here, time didn't begin because the very concept of before is meaningless. Picture Earth's North Pole. Asking what's north of it makes no sense. It's the reference point where directions break down. Similarly, the Big Bang might be a temporal boundary where time itself crystallizes into existence. In this view, the early universe was a four-dimensional sphere with no edges in space or time, blending quantum fuzziness with gravity's grip until classical time emerged like condensation forming on glass. These aren't just abstract thought experiments, they're attempts to answer a haunting question. Why does time have an apparent origin? The Big Bounce offers continuity. The no-boundary proposal offers a cosmic clean slate. Both force us to confront the possibility that our universe's clock might not be the first, or only one ticking in the dark, whether time stretches back forever or curls in on itself like an Ouroboros. One thing's certain, the silence before the Big Bang might be the universe's greatest unsolved riddle. And the answer could rewrite not just cosmology, but our very understanding of existence. The early universe didn't just run hot, it ran slow. During the Big Bang's first explosive moments, time itself oozed like molasses, warped by densities so extreme that a single second stretched into what would now feel like billions of years. This wasn't just a cosmic traffic jam, it was time bending under the weight of reality's most extreme conditions. Picture the entire mass of today's observable universe, 2 trillion galaxies, their stars, planets, and dark matter, crammed into a space smaller than a single atom. Under that kind of pressure, even time had to fight to move forward. Here's how it works. Gravity doesn't just pull on objects, it drags on time. The stronger the gravitational field, the slower clocks tick. Near Earth's surface, the effect is tiny, but in the Big Bang's opening act, when the universe was a seething trillion-degree broth of energy, gravity's grip was unimaginably stronger. Space was so compressed that time dilated to an absurd degree. What we now experience as a heartbeat would have taken eons to unfold back then. The numbers defy intuition. During the Planck epoch, The first 10 to the minus 43 seconds physicists estimate time may have passed 10 to the 32 times slower than it does today. To put that in perspective, if you could somehow survive in that primordial hellscape, the time it takes to blink would encompass the entire current age of our universe over 13 billion years, multiplied by a factor of billions. This extreme slow-motion phase wasn't just a quirk, it shaped everything. Quantum fluctuations, the tiny ripples that eventually seeded galaxies, had what felt like an eternity to imprint themselves onto the fabric of space-time. Inflation, the universe's sudden growth spurt, might have seemed instantaneous to an outside observer, but for the universe itself, it unfolded at a glacial pace. The slower time ran, the more finely tuned those early structures became, setting the stage for everything from galaxy clusters to the chemistry of life. And here's the twist, we're still feeling the echoes of that slowed-down dawn. The cosmic microwave background, the afterglow of the Big Bang, holds subtle temperature variations that reflect time's uneven flow in those first moments. It's as if the universe left us a fingerprint, a frozen record of time struggling to push forward against gravity's vise grip. So when you glance at a clock today, remember, those steady ticks are a luxury. Time didn't always flow this smoothly. It fought its way out of the cosmic deep freeze, second by agonizing second, to give us the rhythm we take for granted. The universe had to endure its own slow motion birth before time could even begin to speed up. The idea of a single, unified timeline might be nothing more than a comforting illusion. According to eternal inflation theory, our universe could be just one bubble in an infinite cosmic foam, a sprawling multiverse where each pocket of reality operates under its own rules of time. Some of these universes might experience time frozen solid, like a glacier in the void. Others could have clocks ticking backward, their futures bleeding into their past. And somewhere out there, an infinity of timelines could be unfolding in directions we can't even fathom. Picture a pot of water boiling violently on a stove. Each bubble rising to the surface represents a newborn universe pinching off from the larger quantum field with its own physics. In this metaphor, time isn't the stove, it's the steam. Some bubbles trap it, locking time in stasis. Others let it rush forward or spiral in reverse. Our universe just happens to have steam flowing in one consistent direction, but there's no rule saying that's universal. In fact, given enough bubbles, every possible configuration of time would emerge somewhere in the multiverse. The implications are staggering. A universe where time is frozen wouldn't even notice. No clocks tick, no thoughts form, no change occurs. It would be a cosmic stillborn, a snapshot of existence trapped in a single moment forever. Meanwhile, a reverse time universe might look bizarre to us, but to its inhabitants it would feel perfectly natural. Eggs would unscramble themselves, shattered glass would leap back into whole panes, and people would remember the future instead of the past, except they wouldn't call it the future. To them, that's just how time flows. Here's where physics gets truly wild. Some theories suggest these bubble universes aren't entirely separate. Quantum entanglement could thread between them, creating fleeting bridges where time's arrow bends unpredictably. Imagine two universes where time runs opposite to each other. Any particles shared between them would appear to move backward in time from one perspective, a phenomenon that might explain certain anomalies in quantum mechanics. It's as if the multiverse is a vast clock shop where every timepiece ticks to its own rhythm, some clockwise, some counterclockwise, some not moving at all. The most unsettling possibility, if eternal inflation is real, there could be regions where time's flow changes mid-universe. Picture a cosmic storm front where the arrow of time flips direction, creating zones where cause and effect reverse. Traveling through such a boundary would be more disorienting than any black hole. One moment you're watching a star age, the next you're seeing it reassemble from stardust. While we can't yet observe these alternate time streams directly, their potential existence reshapes how we view reality. Time might not be a fundamental feature of the cosmos, just a local condition like the temperature of a room in a vast, climate-varied mansion. The multiverse doesn't care about our clocks. It's too busy experimenting with every possible way for moments to unfold. What if you could stroll into the past just by taking a long walk through space? This isn't fantasy, it's a bizarre consequence of Einstein's equations, revealed in 1949 when mathematician Kurt Gödel discovered a solution that permits time loops. Imagine a universe rotating so fast that space itself twists into a helix, allowing you to circle back to your own past simply by following the curve. Gödel's solution sent shockwaves through physics, proving that under extreme conditions, time could fold into a closed loop where cause and effect chase their own tails. These loops, called closed time-like curves, aren't just mathematical oddities. Wormholes, hypothetical tunnels through space-time, could theoretically create them. Picture a wormhole with one end anchored near Earth and the other hurtling away at near light speed. Time would pass slower for the moving end due to relativity, creating a temporal rift. Step through the stationary end today, and you might emerge from the speeding end yesterday. Voila, a bridge to the past. The catch: wormholes require exotic matter with negative energy to stay open, a substance we've never observed. Even stranger, quantum physics suggests these time loops might self-destruct. Calculations show particles traveling back in time could amplify their own energy in a feedback loop, flooding the wormhole with infinite radiation and snapping it shut like a cosmic mousetrap. But here's where the debate gets fierce. Some physicists argue closed time-like curves might avoid paradoxes through self-consistency. Imagine firing a bullet into a wormhole, only for it to exit the past and hit your gun before you pull the trigger. Impossible, not necessarily. The Novikov self-consistency principle suggests the universe would prevent contradictions. Maybe the gun jams or the bullet veers off course. Every action in the loop would adjust subtly to maintain logical harmony, like a cosmic editor trimming plot holes from reality. Others aren't convinced. Stephen Hawking proposed the chronology protection conjecture, a cosmic rule that outlaws time loops to preserve causality. Nature, he argued, might abhor time travel as much as a perfect vacuum. Yet quantum experiments muddy the waters. Particles entangled across time seem to influence each other's past states, hinting that microscopic time loops might already exist. Are these glimpses of a deeper truth or just mathematical artifacts? The answer could reshape reality itself. If closed time-like curves are possible, even in theory, then time isn't a river, it's a Möbius strip where the future and past are two sides of the same cosmic coin. Whether nature allows such loops remains one of physics' greatest puzzles, but one thing's certain: Gödel's spinning universe proved time is far more flexible and far stranger than we ever dreamed. What if nearly 3 centuries of recorded history never actually happened? That's the audacious claim behind the phantom time hypothesis, a fringe theory suggesting the years 614 to 911 AD were fabricated, inserted into the timeline like a cosmic typo. According to German historian Herbert Illig, these missing years were invented by a conspiracy involving Holy Roman Emperor Otto III, Pope Sylvester II, and possibly even Byzantine rulers, all allegedly rewriting history to place themselves at the symbolic turn of the millennium. Imagine erasing 300 years of events, rulers, and cultural shifts with the stroke of a pen. Entire dynasties, wars, and technological advances would vanish into thin air, or more accurately, never existed at all. The theory hinges on perceived anomalies in the historical record. Illig pointed to gaps in architectural styles, inconsistencies in eclipse records, and the suspiciously rapid adoption of the Gregorian calendar as evidence of tampering. Take Charlemagne's reign, often called the Carolingian Renaissance. Illig argued the sheer volume of achievements attributed to this era: legal reforms, literary revivals, military conquest, stretches credibility if squeezed into just a few decades. To him, it reads like someone padding a resume with fictional accomplishments. Even the dating of medieval manuscripts comes under scrutiny. Some parchment appears suspiciously well preserved for documents supposedly 1,000 years old, raising eyebrows among adherents of the theory. But mainstream historians and scientists have dismantled these claims methodically. Radiocarbon dating delivers the most decisive blow. Trees don't lie, their growth rings form an unbroken timeline stretching back millennia. By analyzing ancient wood samples like those from German oak forests, researchers have matched ring patterns to known climatic events, creating a continuous record that leaves no room for a phantom gap. The same goes for ice cores drilled from Greenland's glaciers, where volcanic ash layers align perfectly with documented eruptions from the missing centuries. Even celestial mechanics refute the idea. Astronomers can retroactively calculate past eclipses with precision, and records from China, the Middle East, and Europe all describe the same celestial events during the disputed period, events that would have been impossible to fake across multiple continents. So why does the idea persist? Perhaps because it taps into a deeper fascination with historical uncertainty. Time is slippery, records fragmentary, and power has always bent narratives to its will. The phantom time hypothesis, while debunked, serves as a reminder that history isn't just a collection of facts, it's a story we reconstruct, scrutinize, and sometimes question to the point of unraveling. But in this case, the threads hold firm. The past may be stranger than we think, but it's not quite that flexible. Living in space doesn't just change your surroundings, it rewires your sense of time. Astronauts aboard the International Space Station experience 16 sunrises and sunsets every 24 hours as they orbit Earth, a relentless cycle that obliterates the natural rhythms our bodies evolved to follow. Without the steady march of daylight and darkness, the brain struggles to anchor itself. Minutes blur into hours and days collapse into an amorphous stream of artificial lighting and shifting shadows. NASA psychologists have documented crew members losing track of whether they've been awake for 8 hours or 18, their internal clocks adrift in a sea of perpetual twilight. This temporal disorientation goes deeper than missed bedtimes. The absence of Earth's gravitational pull alters fluid distribution in the body, including cerebrospinal fluid around the brain, a shift some scientists believe could directly impact time perception. In experiments, astronauts consistently misjudge the duration of short intervals, perceiving seconds as longer or shorter than they are. It's as if their mental metronomes have been thrown offbeat by the silence of freefall. Now imagine stepping onto Mars, where the challenges multiply. A Martian day, called a sol, lasts roughly 24 hours and 39 minutes. That extra half hour might seem trivial, but for human brains wired to Earth's precise 24-hour cycle, it's a recipe for chronic jet lag. During NASA simulated Mars missions like HICs in Hawaii, crews living on Mars time reported persistent fatigue as their biological clocks fought against the drifting schedule. Even simple tasks like meal planning or sleep tracking became cognitive hurdles, with exhaustion mounting as the crew's internal rhythms fell further out of sync with the rotating red planet outside their habitat. The strangest effects emerged during long-duration isolation. Astronaut Scott Kelly, who spent nearly a year in orbit, described time becoming stretchy, weeks blending together until he'd forget whether an event happened yesterday or last month. Others report moments of temporal whiplash, like watching 16 sunrises in a single workday while chatting with family living through one sunset back home. These distortions aren't just psychological quirks, they're glimpses into how fragile our perception of time really is when stripped of earthly cues. Mars explorers will face this disconnect on an epic scale. A 3-minute delay in radio signals from Earth means real-time conversations are impossible. Every exchange becomes asynchronous, like texting across centuries. Crews might celebrate New Year's Eve while mission control marks mid-December. their calendars diverging like parallel timelines. Future colonists could even develop new circadian rhythms, their biology adapting to the longer sols over generations until Mars' time feels as natural as Earth's once did. What astronauts and Mars simulations teach us is profound. Time isn't just measured in seconds and minutes. It's woven into gravity, sunlight, and the pulse of our home planet. Take those away, and the universe reveals how deeply our clocks are tied to the world beneath our feet, and how alien time can feel when we step into the void. At the very edge of reality, time might not flow smoothly. It could tick in impossibly tiny, indivisible chunks. The smallest possible unit of time isn't a nanosecond or even a femtosecond. It's Planck time, 10 to the minus 43 seconds, a decimal point followed by 42 zeros and a 1. To grasp how absurdly brief this is, imagine slicing a single second into pieces until you've divided it more times than there are atoms in the observable universe. That's the scale we're talking about. At this level, the very idea of continuous time breaks down, revealing a cosmos that might be pixelated, like a cosmic film reel advancing frame by frame. This concept, called quantum granularity, suggests that time isn't an infinitely divisible river but a staircase with steps so small we've never noticed them. Think of it like a digital screen. Zoom in far enough and the smooth image dissolves into individual pixels. Time might work the same way. Below Planck time, the notions of before and after lose meaning, just as you can't have half a pixel on your phone. The universe itself might operate in these discrete ticks, with reality updating like a cosmic GPU rendering existence one Planck-length frame at a time. What does this look like in practice? Enter the bizarre world of quantum foam. At scales this small, space-time isn't calm and orderly. It's a seething, turbulent froth where microscopic black holes and wormholes blink in and out of existence. Gravity becomes so warped that space and time twist into knots, making it impossible to define events with perfect precision. It's like trying to measure the surface of a boiling pot of water with a ruler. The closer you look, the more chaotic it gets. In this realm, time isn't just granular, it's foamy, unstable, and utterly unpredictable. The implications are staggering. If time is pixelated, then the universe itself might run on a kind of quantum clock, with each tick marking a fundamental update to reality. This challenges Einstein's vision of space-time as a smooth fabric, suggesting instead that it's more like a woven tapestry stitched together from indivisible threads. Some theories even propose that these Planck-scale fluctuations could allow microscopic time loops, where particles briefly travel backward before continuing forward, a glitch in the cosmic code. Yet here's the catch: we can't directly observe Planck time. The energy required to probe such scales is trillions of times beyond what our most powerful particle colliders can achieve. It's like trying to hear a whisper from across a hurricane. But the math hints at its existence, and if true, it means our experience of time's flow is an illusion, a shadow cast by something far stranger happening beneath the surface. So the next time you check your watch, remember, those smooth moving hands are masking a hidden quantum heartbeat. Time might not be a river but a flipbook, and we're only just beginning to glimpse the pages. 13.8 billion years, that's the official age of our universe, calculated from the afterglow of the Big Bang. But what if that number is just a local quirk, a timestamp that only applies to our tiny corner of reality? Beyond the cosmic horizon we can observe, time might stretch back infinitely, with universes far older than ours bubbling in the void like ancient cities lost to history. This isn't science fiction, it's a serious implication of cosmic inflation theory, which suggests our observable universe is just one patch in an endlessly larger multiverse, each with its own timeline. Think of it like standing in a foggy meadow. You can only see a few hundred feet in any direction, but that doesn't mean the meadow ends where your vision does. The cosmic microwave background, our window into the early universe, is like that fog. It marks the limit of how far light has traveled since the Big Bang, creating a visible universe bubble. But inflation implies space expanded faster than light in those first moments, meaning there's vastly more universe beyond what we'll ever see. And in those unseen regions, time could have been ticking for trillions of years before our Big Bang even happened. Here's where it gets radical. Some models of eternal inflation propose that new universes are constantly budding off from a quantum foam, each with its own laws of physics and its own starting clock. Ours might be 13.8 billion years old, but a neighboring universe could be infinitely ancient, its timeline stretching back with no beginning at all. Imagine a cosmic tree where each branch is a universe, some young and green, others gnarled with age. We're just one leaf on that tree, oblivious to the centuries that came before our sprouting. Even within our own universe, time might not flow uniformly. Dark energy's acceleration could mean distant regions age at different rates, like clocks in separate time zones drifting out of sync. Galaxies racing away from us at near light speed due to cosmic expansion would experience time dilation, their seconds passing slower than ours. From their perspective, were the ones moving in slow motion. This relativity of time on a universal scale means the age of the universe might be as subjective as asking, what time is it on a train speeding past? So why does 13.8 billion years feel so concrete? Because it's the only timeline we can measure. The light reaching us tells a story that begins with the Big Bang, but the book might have prologues we'll never read. If other universes exist, or if ours is far larger than we can observe, then time itself becomes a local phenomenon, not a universal truth. Our cosmic clock isn't broken. It's just one tick in a grander, older, and far stranger metronome we're only beginning to imagine. What if time isn't a thing at all, but just an illusion conjured by the movement of everything around us? That's the radical idea at the heart of physicist Julian Barber's theory. Time doesn't exist as a fundamental force, it's simply the name we give to the fact that things change. Imagine a universe frozen in a single, perfect instant. No atoms vibrating, no planet spinning, no light waves rippling through space. In this absolute stillness, would time still pass? Barber's answer is a resounding no. Without change, there's no before or after. Just an eternal snapshot, like a paused movie frame mistaken for a story. To grasp this, picture a clock. The hands move, the gears turn, and we call that progression, time. But Barber argues the clock isn't measuring some invisible river flowing through the universe. It's just tracking its own mechanical changes relative to other changes, like Earth's rotation or your heartbeat. Strip away all motion and the clock becomes a meaningless sculpture. Time, in this view, isn't a backdrop to reality. It's a side effect of reality's ceaseless rearrangement. Take this further with a thought experiment. Suppose you could pause the entire cosmos down to the last quark. No particle interactions, no energy transfers, just perfect silence. In that state, how would you measure time? There'd be no ticking atoms in atomic clocks, no pulsars flashing in deep space, no biological processes to mark the hours. You could wait 1 trillion years in this frozen state, and upon unfreezing, no experiment could prove any duration had passed. Without change, time loses all meaning. This challenges our deepest intuitions. We think of time as a stage where events unfold, but Barber flips the script. Events are the stage. His timeless physics suggests the universe is better described as a series of static configurations, what he calls nows stacked like pages in a book. Our sense of flow comes from flipping through these pages, each now subtly different from the last. The passage of time is just our brains stitching these snapshots into a narrative, like a flipbook creating the illusion of motion. Critics argue this reduces time to a psychological trick, but Barber's math holds up. In general relativity, Einstein showed time is malleable, bending around mass and motion. Quantum mechanics, meanwhile, struggles to define time at microscopic scales. Barber's insight bridges these gaps by suggesting time emerges from the relationships between events, not the other way around. Even entropy, the universe's march toward disorder, might just be a statistical trend in how nows arrange themselves, not proof of time's arrow. The implications are dizzying. If time is change, then immortality might look less like living forever and more like freezing all transformation, a paradox where you'd never experience the eternity you've achieved. It also reshapes how we think about the Big Bang. Instead of an explosion in time, the beginning could be a single now bursting into countless others, like a stone dropped into a pond generating ripples of change. So the next time you check your watch, ask yourself, are you measuring time or just the whirl of gears inside a tiny machine? Barber's theory doesn't just tweak our clocks, it threatens to dismantle them entirely, revealing time as a shadow cast by the dance of the cosmos. And if he's right, the universe isn't in time, it is time, one fleeting moment at a time. What if time didn't just move forward and backward but sideways? String theory, the mind-bending framework that proposes extra dimensions beyond our familiar four, suggests that time might not be confined to a single arrow. In higher dimensions, time could branch, loop, or even flow in directions we can't begin to fathom. Imagine a universe where instead of one timeline, there's a sprawling web of them, each with its own past, present, and future, some running parallel to ours, others intersecting at cosmic crossroads. Think of it like a book with pages stacking not just left to right, but up, down, and diagonally. In our three-dimensional world, we experience time as a single thread, a straight line from birth to death. But in a higher dimensional space, that thread could weave through reality in ways that defy all intuition. A being living in, say, 5 dimensions might perceive time as a landscape with peaks, valleys, and even forks where alternate versions of events unfold simultaneously. Here's where it gets wild. Some string theorists propose that these extra dimensions could host entirely independent time arrows, like separate rivers flowing in different directions. In one dimension, time might tick forward as we know it. In another, it could spiral backward or even pulse in and out like a heartbeat. This isn't just sci-fi speculation, it's a mathematical possibility emerging from the equations. If true, it means our universe's timeline is just one slice of a much larger, more convoluted temporal structure. Consider parallel timelines. In a higher dimensional framework, every decision you've ever made, every path taken or not taken, could exist as a separate thread woven into the fabric of reality. What feels like the present to us might be just one frame in an infinite dimensional movie, where alternate versions of history play out in directions we can't access. Quantum mechanics already hints at this with superposition, where particles exist in multiple states until observed. Higher dimensional time could take that further, suggesting entire universes where time branches like a fractal, each with its own unique flow. But how would this even work? One clue comes from closed time-like curves, those hypothetical loops in spacetime that could allow time travel. In higher dimensions, these curves might not just circle back on themselves. They could branch into entirely new temporal pathways, like a subway system with infinite routes. A civilization advanced enough to navigate these dimensions wouldn't just travel to the past or future. They might step into timelines where time itself behaves differently, where cause and effect don't follow our rules, where the very concept of now becomes meaningless. The implications are staggering. If time is multidimensional, then free will takes on a new complexity. Are our choices truly ours, or do they ripple across countless unseen timelines? Could we, in theory, interact with these alternate flows of time? The math doesn't yet have answers, but it paints a picture of reality far stranger than we've dared to imagine. A cosmos where time isn't a river, but an ocean with currents flowing in every conceivable direction. So the next time you feel the weight of a ticking clock, remember, that second hand might be moving in more ways than you think. Our linear experience of time could be just a shadow of something infinitely richer, a single note in a symphony of temporal dimensions we're only beginning to dream of. In a lab at the University of Maryland, scientists did something that sounds impossible. They created a crystal that doesn't just exist in space, but in time. These are time crystals, structures that pulse rhythmically without any energy input, defying one of the most sacred laws of physics, the inevitable march toward entropy. The breakthrough came in 2016, when researchers used chains of ytterbium atoms trapped in diamond-like arrays, chilling them to near absolute zero. Under these extreme conditions, something magical happened. The atoms didn't settle into stillness. They began flipping their quantum states back and forth, ticking like a clock that never winds down. What makes time crystals so revolutionary is their defiance of equilibrium. Normal crystals, like diamonds or snowflakes, are stable arrangements of atoms in space. Their beauty comes from their stillness. But time crystals are stable patterns in time, oscillating between configurations indefinitely without losing energy. It's as if you spun a top and it never stopped, not because it's perfectly efficient, but because the universe grants it a loophole. This isn't perpetual motion, it's a quantum dance where the choreography never fades. The secret lies in what physicists call broken time symmetry. Most physical systems, when you shake them, respond immediately and then settle. But time crystals are stubborn. They respond at a different rhythm than the force applied, like a drummer playing off beat. No matter how you conduct, hit them with a laser pulse and they'll flip their spins every other pulse, creating a cadence all their own. This rhythmic rebellion means they're not just crystals, they're clocks built into the fabric of matter itself. Practical uses: quantum computing is the big one. Time crystals' resistance to entropy makes them ideal for error-proof qubits, the fragile building blocks of quantum machines, but the deeper implications are cosmic. If matter can encode time in its structure, could there be natural time crystals lurking in neutron stars or the primordial plasma of the early universe? Some theorists even speculate that spacetime itself might have time crystal-like properties at cosmic scales, ticking in rhythms we've yet to decipher. The most mind-bending part: time crystals don't just challenge our understanding of matter, they rewrite the rules of existence. In a universe where everything decays, they're islands of perpetual order, whispering that time might be more than a backdrop. It could be a material, something we can shape, even stitch into the quantum world like golden threads in a tapestry. They're not just laboratory curiosities, they're cracks in the facade of reality, revealing glimpses of a deeper physics where time doesn't just pass. It sings. Deep in the fabric of space-time, remnants of the universe's violent birth might still linger, cosmic strings, theoretical defects thinner than an atom but stretching across the cosmos like cracks in frozen ice. These bizarre structures, if they exist, carry unimaginable density, packing the mass of entire stars into lengths thinner than a proton. And here's where it gets wild: their gravitational pull is so intense, they don't just bend space, they twist time itself into knots, potentially creating loops where the future and past stitch together like threads in a Möbius strip. Imagine a cosmic string as a razor-straight scar left over from the Big Bang's cooling phase, when the newborn universe underwent a violent phase transition, like water freezing into ice but on a cosmic scale. These defects didn't smooth out with the rest of spacetime. They stayed behind as tangled relics, invisible yet unimaginably powerful. Now picture two of these strings parallel to each other, racing past one another at nearly the speed of light. The spacetime between them would undergo such extreme warping that closed time-like curves, those time loops we've talked about, could form naturally. Fly a spaceship around these moving strings in just the right way, and you might return before you left, like a needle stitching backward through the fabric of reality. The math behind this is both elegant and eerie. Einstein's equations show that massive moving objects drag spacetime around them like a boat creating ripples in a pond. Cosmic strings take this to the extreme. Their infinite density means they don't just create ripples, they carve canyons in space-time, bending it so severely that time itself circles back on itself. It's as if the universe left behind tiny, hypercharged time machines in its infancy, hidden in plain sight. But don't pack your bags for a temporal joyride just yet. While the theory is sound, no one's ever detected a cosmic string directly. Their ghostly signatures might reveal themselves through bizarre gravitational lensing, distorting light from distant galaxies into double images, or via bursts of gravitational waves. Some physicists even suggest that the faint, unexplained glitches in pulsar timing arrays could be echoes of strings vibrating across the cosmos. Here's the cosmic irony. If these strings exist, they're likely remnants of a time before time as we know it even settled into a steady flow. They're relics of an era when the universe was so hot and dense that the very concepts of before and after were still congealing. And yet, they might hold the key to unlocking time travel, turning the universe's ancient scars into gateways to its past and future. So while we haven't found them yet, the hunt for cosmic strings isn't just about proving a wild theory. It's about testing whether the universe left us hidden tunnels through time itself. And if they're out there, woven into the dark tapestry of space, they're a reminder that reality's rulebook might be far more flexible than we ever dared to dream. The Big Bang is often called the birth of time itself, but that idea hides a paradox so deep it threatens to unravel our understanding of cause and effect. Think about it. If time began at the Big Bang, what caused it to start? Causality requires time. An event must come before its effect. But without time already flowing, how could something trigger the universe into existence? It's like trying to light a match before matches were invented. Some physicists argue this reveals a flaw in how we picture the Big Bang. Maybe time didn't begin at all. Loop quantum gravity, a leading theory attempting to unify quantum mechanics and relativity, suggests the Big Bang wasn't a true singularity, a point of infinite density, but a bounce from a previous universe collapsing. In this view, time doesn't start or stop, it cycles like a cosmic heartbeat. Picture a slinky stretching and compressing endlessly. The moment we call the Big Bang might just be the transition from contraction to expansion, with time flowing continuously through the squeeze. Even stranger are timeless quantum gravity models, which erase time from the equations entirely. At the quantum level, particles don't experience time as we do. They exist in superpositions, entangled states where before and after lose meaning. Theories like Julian Barber's nows propose that time emerges from quantum correlations, like a movie reel creating the illusion of motion. In this framework, the Big Bang isn't an event in time. It's a quantum leap between configurations of the universe, where time crystallizes from timelessness like ice forming on a pond. The implications spiral outward. If time is emergent rather than fundamental, then asking, what came before the Big Bang, might be as nonsensical as asking, what's north of the North Pole? There's no before in a timeless quantum soup, just a reshuffling of probabilities. This reshapes the paradox. Instead of time beginning, perhaps our perception of it condensed from a deeper, timeless reality, like steam settling into droplets. Yet the mystery only deepens. Even if time emerges, what triggers its emergence? Why does it flow in one direction? Each answer peels back another layer, revealing how profoundly we've underestimated time's enigma. The Big Bang might not be time's origin story, just the moment our cosmic clock started ticking in a far grander, stranger symphony we're only beginning to hear. Hollywood often bends time to its will, but some films get startlingly close to the real physics of time dilation. Take Interstellar, where the crew lands on Miller's planet, orbiting the supermassive black hole Gargantua. As they struggle through knee-deep water and monstrous waves, every hour on the surface costs them 7 years back on the ship. This isn't just dramatic license, it's a near-perfect depiction of gravitational time dilation. Black holes warp spacetime so intensely that clocks near them tick slower relative to those farther away. The film's science consultant, Nobel Prize-winning physicist Kip Thorne, ensured the math was airtight. Gargantua's spin and mass were calculated to create exactly that time-stretching effect, making it one of the most scientifically accurate portrayals of extreme relativity ever put on screen. But not all time-bending films rely on cosmic monsters. Arrival takes a subtler approach, exploring nonlinear time through language. When linguist Louise Banks learns the alien heptapod's circular script, her mind begins rewiring to perceive time as they do, not as a straight line, but as a tapestry where past, present, and future interweave. This mirrors real theories about consciousness and time. Some neuroscientists suggest our perception of time's flow is deeply tied to how we structure language. The film's twist that Louise's memories of her daughter are actually glimpses of a future she hasn't lived yet echoes quantum mechanics' block universe theory, where all moments exist simultaneously. Then there's Tenet, where time runs backward for entire sequences. While inversion breaks thermodynamics in reality, the film's portrayal of reverse entropy isn't entirely fantastical. At the quantum level, particles like kaons exhibit time reversal symmetry, behaving identically whether time flows forward or backward. The movie exaggerates this into a weaponized paradox, but the seed of the idea comes from genuine physics. Even the protagonist's disorientation mirrors how physicists feel when grappling with equations that work equally well in either time direction. The irony. Many sci-fi films stumble on the simplest time dilation effects. In The Flash, Barry Allen runs so fast he time travels, but relativity says extreme speed slows time for the traveler, not speeds it up. Avengers Endgame hand waves quantum time travel with PIM particles, while real quantum mechanics offers no such shortcuts. Yet these inaccuracies highlight a deeper truth. Time is so counterintuitive that even storytellers bend it in ways that feel right emotionally, even when they clash with known physics. What makes Interstellar and Arrival stand out is their refusal to treat time as a mere plot device. They let its strangeness linger, forcing audiences to sit with the same discomfort Einstein once did when he realized time isn't absolute. Whether through a black hole's gravitational grip or the rewriting of human cognition, these films don't just entertain, they invite us to experience time as the universe understands it, malleable, mysterious, and far beyond the ticking of a clock. The holographic principle turns our understanding of reality inside out. What if time isn't a fundamental feature of the universe, but a flickering projection from a hidden two-dimensional surface? Imagine the cosmos as an enormous movie screen where every event we perceive, from supernova to the ticking of a clock, is just light playing across the surface of something far simpler. According to this radical idea, born from black hole physics and string theory, all the information needed to construct our three-dimensional world, including the flow of time, might be encoded on a distant, flat boundary like data etched onto a cosmic DVD. And if that's true, then time as we know it could vanish as suddenly as a projector being switched off. This isn't just poetic metaphor, it's grounded in the physics of black holes. When matter falls into a black hole, it doesn't just disappear. Quantum mechanics insists the information it carries must be preserved, leading theorists like Gerard T. Hooft and Leonard Susskind to propose that all the data about what's inside the black hole gets smeared across its event horizon, the point of no return. This horizon is a two-dimensional surface, yet it somehow encodes the complete three-dimensional reality of everything within it. Extend this idea to the entire universe, and you get the holographic principle. Our 3D cosmos might be a shadow cast by quantum interactions playing out on a distant 2D boundary we can't see. Time enters the picture in a bizarre way. If our experience of time emerges from how that 2D data is processed like frames in a movie being projected in sequence, then altering the projection could fundamentally change how time behaves. In some holographic models, time isn't built into the underlying code of the universe. It's more like an illusion created by how the data unfolds. This means under extreme conditions, like near the singularity of a black hole or in the very early universe, the projector might glitch, causing time to stutter, loop, or even stop altogether. It's as if the universe has a pause button we've never noticed. The implications are dizzying. If time is emergent rather than fundamental, its flow isn't guaranteed. Some theories suggest that in a hypothetical holographic phase transition, a shift in how the cosmic data is processed, time could literally switch off, freezing the universe like a buffering video. Particles would stop moving, thoughts would cease mid-sentence, and entropy's relentless march would halt, not because everything reached absolute zero, but because the rules generating time's arrow simply stopped running. Could this ever happen? The math allows for it, though we've never observed anything like it. Yet the holographic principle offers a chilling reminder: time might be more fragile than we ever imagined. Not a river, not a dimension, but a fragile construct flickering into existence one projected moment at a time, and just as easily it could blink out. Hidden in the microscopic world are creatures that bend time's rules to their will, like the tardigrade, a half-millimeter-long organism that can survive the vacuum of space, extreme radiation, and temperatures near absolute zero. But their most astonishing trick isn't just enduring these extremes, it's how they seemingly slow down their own biological clocks to a crawl. When dehydrated, tardigrades enter a state called cryptobiosis, curling into a lifeless speck called a ton. In this form, their metabolism drops to 0.01% of normal, suspending biological time so completely that they've been revived after 30 years in this frozen state. For all practical purposes, they hit pause on their existence, then reanimate as if barely a day had passed. Now imagine applying this to human space travel. Astronauts journeying to distant stars face an impossible hurdle. Even at light speed, interstellar voyages would take centuries. But what if they could borrow the tardigrade's playbook? Scientists are already exploring induced torpor, a form of controlled hibernation, to slow human metabolism during long missions, lower body temperature, reduce oxygen demand, and you might stretch a 7-month trip to Mars into a subjective blink for the crew. The European Space Agency's studies suggest cooling astronauts to around 32 degrees Celsius could mimic aspects of hibernation, dialing down cellular activity like a computer throttling its processor to save power. But here's where it gets surreal. Combine torpor with relativity's time dilation, and the effects multiply. A crew in hibernation, traveling at near light speed, would experience dual time slippage. Their slowed biology and physics clock slowing effect could make a century-long trip feel like weeks on board. Picture a generational starship where awake crew members age decades while hibernating astronauts barely tick forward, emerging to find their colleagues gray-haired or gone. It's a biological twist on the twin paradox, not just clocks diverging, but lived experience splitting across time zones of flesh and blood. The challenges are colossal. Human hibernation isn't like flipping a switch. It risks muscle atrophy, bone loss, and brain damage. Yet nature offers clues. Arctic ground squirrels survive winter with body temperatures below freezing, their brains somehow protected from ice damage. Black bears hibernate for months without losing bone density, their bodies recycling waste into nutrients. Cracking these secrets could turn sci-fi stasis pods into reality, rewriting deep space travel from a marathon of endurance into a single, timeless leap. For now, tardigrades remain the masters of biological time travel, proof that life can hack the universe's clock. Their existence whispers a tantalizing possibility. Time isn't just something we pass through. It's something we might one day learn to control, not with engines or wormholes, but with the silent, ancient wisdom of our own selves. Is time something our brains create, or is it woven into the fabric of reality itself? This ancient philosophical debate pits thinkers like Immanuel Kant, who argued time is purely a mental framework, against modern physicists who treat it as a fundamental dimension of the universe. Kant famously claimed time isn't out there, it's the lens through which we organize sensory input, like a mental filing system for events. Your brain doesn't perceive time so much as invent it, stitching together moments like frames in a movie reel to create the illusion of continuity. Modern neurology reveals how fragile this illusion really is. Patients with damage to the suprachiasmatic nucleus, the brain's master clock, lose the ability to gauge durations accurately. Psychedelics like psilocybin can compress or stretch subjective time, making minutes feel like hours. Even mundane activities warp perception. A car crash survivor might describe the event unfolding in slow motion, their amygdala flooding with adrenaline to hyper-focus their memory. These distortions suggest time as we experience it isn't an objective flow, but a constructed narrative heavily edited by our biology, yet physics tells a different story. Einstein's relativity treats time as a geometric dimension, interwoven with space and measurable down to Planck scale intervals. Atomic clocks tick with precision whether humans observe them or not. The cosmic microwave background preserves a timeline stretching back billions of years, long before consciousness existed. If time were purely mental, how could black holes dilate it or GPS satellites require relativistic corrections? The tension between these views birthed radical theories. Some quantum gravity researchers propose time emerges from quantum entanglement, a collective effect of particles correlating their states. Others, like neuroscientist Dean Buonamano, suggest the brain approximates time through state-dependent networks, where neural patterns evolve in predictable sequences, creating a proxy for temporal flow. In this hybrid model, time might be fundamental at cosmic scales, but our experience of its passage is a clever neurological hack. Perhaps the truth bridges both extremes. Just as color doesn't exist without photoreceptors to interpret wavelengths, time may require minds to give it meaning. The universe provides the raw material, events unfolding in sequence, but consciousness sculpts those events into stories with beginnings, middles, and ends. Without brains to register it, time might still exist, but it wouldn't be felt, remembered, or feared. It would just be a silent clock ticking in an empty room, measuring changes no one witnesses. This duality reshapes how we see reality. Time isn't just out there or in here, it's the dance between the world's rhythms and the stories we tell about them. Your sense of now, your nostalgia for the past, your anxiety about the future, they're not just reactions to time, but part of what time is. The universe gives us the beats, but consciousness writes the music. Time doesn't just flow, it could one day evaporate, freeze, or even shatter. The ultimate fate of time hinges on how the universe itself ends, and physicists have proposed scenarios so bizarre they make black holes look mundane. At one extreme lies heat death, the slowest and coldest apocalypse imaginable. Picture a universe where all stars have burned out, black holes have evaporated, and every particle drifts endlessly apart in an ever-expanding void. Entropy reaches its maximum, no energy gradients, no motion, no change. In this frozen wasteland, time doesn't so much end as become meaningless. With nothing left to measure, no clocks to tick, and no events to sequence, time's arrow dissolves into silence. It's not an explosion or a collapse, just an infinite, featureless stasis where the very concept of now loses all relevance. But heat death isn't the only way time could bow out. Vacuum decay offers a far more violent finale. Imagine the universe resting on a precarious quantum ledge like a marble balanced atop a hill. Right now, our vacuum seems stable, but some theories suggest it might be a false vacuum, a temporary low-energy state. If a tiny patch of space were to suddenly tunnel into a lower-energy, true vacuum, it could trigger a catastrophic bubble expanding at light speed. inside this bubble, the laws of physics rewrite themselves. Constants like the speed of light or Planck's length might change instantly. Time as we know it would cease to function. Atomic bonds could dissolve, matter reconfigure, and causality itself unravel in a cosmic reboot, the scariest part. This could already be happening somewhere beyond our cosmic horizon, and we'd have zero warning before the bubble wall hits. Then there's the big crunch, a dramatic rewind of cosmic history. If dark energy weakens and gravity regains dominance, the universe could reverse its expansion, collapsing back into a singularity. Time wouldn't just end here, it might loop. Some models suggest a new Big Bang could emerge from the collapse, birthing a fresh universe with its own arrow of time. But would this new timeline remember its predecessor, or is each cycle a blank slate? The math allows for both possibilities, leaving us to wonder if time is a one-act play or an endless season with repeating themes. But what if time doesn't end? What if it transforms? Quantum gravity theories hint that near the universe's final state, time might shed its classical nature entirely. It could fracture into discrete chunks, dissolve into probabilistic foam, or even merge with space so completely that when and where become indistinguishable. In some brain cosmology models, our dying universe might collide with another higher dimensional membrane, injecting energy that resets time's arrow like a cosmic defibrillator. The most haunting question isn't just how time ends, it's whether end even applies. If the block universe theory is correct, where past, present, and future exist eternally, then time's demise might be an illusion. The Big Bang, heat, death, and every moment in between could coexist like pages in a book, unchanging. Our fleeting sense of time's flow would just be a quirk of perception, a flickering consciousness moving through a static tapestry. So while we worry about deadlines and ticking clocks, time itself might be playing a far grander, stranger game. Whether it fades, loops, or transcends entirely, one thing's certain: the last second of the universe will be nothing like the first. And in that final moment, if anyone's left to count it, time might just reveal its greatest secret, that it was never what we thought it was at all. From black holes freezing time to quantum particles ignoring it altogether, we've journeyed through a reality where clocks are liars and seconds are shape-shifters. Gravity doesn't just bend light, it warps time like taffy, stretching a single minute near a black hole into years elsewhere. Speed rewrites your personal timeline, meaning astronauts literally time travel into the future, even if just by microseconds. And at the quantum level, time might not even exist as we know it, just a blur of probabilities where particles teleport through moments like ghosts walking through walls. Then there's the cosmic horror show, entire universes where time runs backward, or the spine-chilling possibility that our past, present, and future are already written into the fabric of space-time like chapters in a book we can't put down. Even the Big Bang might not have been the beginning, just a reboot in an endless cycle of cosmic resets. So here's the kicker: everything you think you know about time is probably wrong. Your morning alarm, your calendar, even the aging of your own body, they're all illusions crafted by a universe that plays fast and loose with the rules. Time isn't a steady river, it's a funhouse mirror, a hall of smoke and mirrors where the only constant is how wildly it can deceive us. Now it's your turn. What's your wildest theory about time? Do you think it's all an illusion, or is there some cosmic clock ticking behind the scenes? Drop your mind-bending ideas in the comments. We're obsessed with this stuff. And if you're hungry for more cosmic mysteries, hit that subscribe button. The universe has way more secrets to spill, and we're just getting started.